Hello and welcome everyone to this live stream presentation. I think we're going to have a lot of fun today. It's going to be a conversation that pulls together a few different threads, a few different people, a bunch of technologies, and it's going to lead to some interesting takeaways, including, spoiler alert, that engineering is a team sport and can be a lot of fun. So there's going to be a bunch of people here today, and if you want to show the mug shots of us there. And it's interesting that it looks like a few of us are still using our high school or at least college mug shots, but there's going to be plenty of time for everybody here to talk. So I'm just going to go quickly through. My name's Greg Brown. I'm from Onshape. I've got Dan Kirchgessner from Formlabs, Daniel Riley from RCTestFlight, and Austin Holbrook from Holbrook Aerospace. As I said, there's going to be a conversation between all of us. And so let's get straight into it. And I'll tell you what we're going to do here today. So it all started with a viral YouTube video, and we're going to dig into that and how Daniel is behind that. We're going to look at what was built as part of that video, who got involved, how the design worked, how it got created, and a lot of takeaways from that whole process. And as I said before, engineering as a team sport, as a big collaboration, and a lot of fun was had along the way. Now, there's going to be time for Q&A at the end. So please queue up your questions, ask in the chat, and we will get to all of that as we go through. But the first thing here, we're going to bring Daniel on. And Daniel, you've got a lot of YouTube followers. Tell us a little bit about RCTestFlight and what's going on here.
Yeah, so RCTestFlight is just a channel that I started when I was a kid, basically back in 2009, just building RC planes and crashing them and repeating the process. And I just kind of never stopped. And now it's turned into my full-time job. So I'm super grateful for that. And it's been an awesome journey.
It seems like a lot of people are interested in that too. So a competition you hosted, conceived this competition. What was it all about?
Yeah, so this whole propeller thing kind of started back about 2 years ago. MIT released this video about toroidal propellers, and the internet kind of at large misinterpreted that video and to thinking that toroidal propellers were going to be like this amazing revolutionary new technology that was going to change transportation as we know it. And I was very suspicious of that. So I started kind of designing some little toroidal propeller models and testing them out. And the videos that I made, those propellers did really well. So I figured, geez, people really like these propellers. I should kind of outsource the propeller design to the community and just, test what people submit. And that's kind of what started it all.
Yeah, I mean, I actually can spy a couple of toroidal propellers in that little gallery you've got there. And I do remember that was kind of like a viral moment that you don't always get in engineering on YouTube. So, the whole toroidal propeller peak toroidal propeller we had was kind of an interesting thing. So the idea was that people would send you designs, is that right?
Yeah, the first few toroidal propellers that I tested were really bad, not because toroidal propellers are bad, but just because I'm a propeller design expert. So I figured if I just outsource the propeller design to the community, surely someone out there actually knows what they're doing and can design something that has a good chance at working well. And that would give me a better idea of, whether there's actually something to the toroidal propeller idea. So yeah, it was just about outsourcing the design to others.
Sure, good. Get someone else to do the work. That's great. So what's going on in the right-hand side there up the top there? You've got some kind of test rig, is that right?
Yeah, so that's a boat I built a couple years ago, and for this propeller design competition, I retrofitted it a load cell to measure thrust and a GPS to measure speed, and we're basically using that to run each propeller through a waypoint mission, a GPS-guided waypoint mission, and we'll collect data and basically compare the grams of thrust per watt for each propeller, and that's our efficiency measurement. And then, we rank all 50 propeller submissions and find a winner.
So we're looking at some telemetry or some analysis down on the bottom of the screen there, right? You tested, it looks like your baseline against somebody's, let's let submission there, right? So you're looking at efficiency.
Yeah, basically the way I did it, and I would change this in the future if I do it again, but We measured gram thrust per watt over a speed range, because propellers are designed to perform best at a single speed. So it's not fair to compare a bunch of different propellers all at one speed, because some might bias, some might perform better at higher speeds, some might prefer at low speeds. So I figured it'd be best if we could kind of compare them over a larger speed range. So it's basically measuring the area under the curve, and that's how we find the winner.
I think this also triggered a lot of engineering and data nerds online that this is something they really wanted to see. That's why it's probably got over 2 million views at a bunch of months ago. So talking of community and talking of other people, let's bring in Austin at this point. Austin, welcome.
Thank you.
Hey, and so Daniel for some time. Tell us a little bit about how this got all hooked up together.
Yeah, so I published my book last year, and I've kind of been evangelizing it since then. So I contacted Daniel earlier this year and told him about my book and what it could do, and kind of just gained ground steadily as he became more interested in it. I sent him an airfoil, just an airfoil you could update. And then he was at this time mentioning he was setting up the competition, looking for a way that he could allow his community to kind of vary the propeller design. So Onshape was really helpful, because I could immediately adapt all the ideas from my book right into Onshape, because the design table was just allowed you to easily automate anything.
So what we're looking at here on screen is the Onshape model, right?
That table on the right is essentially just all information from the book, and it started out as one airfoil, and then Daniel and I one day got and in one day we did the baseline propeller, and it was in the first couple of videos, it's mostly some variations of the baseline propeller, and you can see like what kind of improvements he got just from this one model without the whole community chiming in. And that was kind of interesting, because the best version of that was the kind of baseline for the rest of the competition. So in one day, essentially, we took that adaptable airfoil model, put it in a more complicated part where there's several airfoils in combination, and then made a modular propeller. And I still remember Daniel being excited about like how the tip rebuilt, the swept tip rebuilt every time. And he just said, so we just had a lot of fun with it since then.
Okay, so you guys were collaborating on this, just with this baseline design. You also, it seems to be, and looking at it, you've made this public, right? So this is a document in Onshape that other people can access.
Mm-hmm. Correct. Yeah, there's some more complicated versions on my site, but they're now kind of antiquated by the feature that we've developed. They're still interesting because they show kind of the mechanics of how the current feature works.
Yeah.
But
sure.
And
a bunch of people,
to see how far we can go beyond that.
Yeah. So a bunch of people who were going to submit designs to Daniel's competition accessed this model online and went crazy with it, right? And did their own thing.
Yeah. And it's amazing, like just with the design, you'd think the design table would be a little bit clunky, but people just worked with it. I think like 80% of the models, between 50 and 80% of the models use this template. This was really interesting to see.
So Daniel, you were pretty amazed by the different variety of things people were coming up with or dreaming up, with their propellers. Some toroidal ones, of course, but
yeah, a lot of very creative people out there. And that's kind of one of the reasons why I really wanted to start off this competition by developing a space propeller, because, and one of the big takeaways that I have from just propeller testing in general is it's so important to match the size and the pitch of the propeller with the motor. Like if the motor outputs a certain amount of torque, and if you're not perfectly catering that propeller to that motor, then the whole system is going to be terribly inefficient. So the purpose of this baseline propeller was just to give people a good starting point to kind of, intuitively like look at the size of the baseline propeller and say, okay, I need to design my propeller to have roughly this amount of bite, this amount of flotation resistance in the water. And my hope was that would prevent people from submitting, all sorts of just crazy propellers that would have no chance of matching up the motor that I was using for the competition. So
okay, cool.
Yeah, it served its purpose.
Yeah, so I mean, I can see why this has already triggered a bunch of engineers and scientists and hackers and makers and people interested in data. You know, it's sort of, it ticks a lot of the boxes with why it was so interesting, and so many people went to watch it and submit their own designs too. It was pretty impressive. So we've got the competition. We've got people uploading digital CAD, hopefully using Onshape, right, and using this baseline, and then going crazy. But of course, you need to get them bolted onto the test motor and put them in that test rig. That takes a lot of serious building skills, right? And Dan, I think this is your area. So welcome, Dan, and tell us a little bit about how you got involved with Daniel and this whole competition. And yeah.
Yeah, thank you so much. Yeah, I'm Dan Kirchgessner. I'm the partnerships manager here at Formlabs. And yeah, the way this came about was pretty natural and organic and really great. So we had been talking to the Onshape team about content creators they were working with, and Daniel's name came up. This was probably a year and a half ago. And at that time, we had the Form 3, our third generation of our SLA 3D printer out, and we sent one to Daniel. He got some good use out of it. But earlier this year in April, released the Form 4, which is our newest machine. It's much faster, and that we sent that one to Daniel as well to try out. And the timing happened to line up quite nicely with this propeller design competition. So yeah, he was able to iterate quite quickly on these designs, which, as you guys were just mentioning, and I'll use that to jump into kind of how Formlabs is involved. We make 3D printers. Obviously, to make a physical object, you need a way to produce it, but you can't produce a part without that 3D file first. So you start with the 3D file, then you start to think about production. And propellers, more than a lot of other kind of industrial design worlds, are all about iteration. As Daniel and Austin were just saying, there is a lot of steps of trying something, seeing how it works at a specific RPM and torque value, and then going back to the drawing board and trying it again and again and again. So yeah, when we released a printer where the whole point was to iterate quickly and iterate multiple designs during a single day, it seemed like a really perfect match.
So it looks like, I mean, in that bottom right-hand corner, there's a bucket of lots of Form 3 printed propellers there, I think. Do you have any idea how many Daniel created, including the iterations? I mean, it seems like it's going to be a lot.
I don't actually. And when Daniel jumps back on, I'd love to know sort of if he has a rough total part quantity to hear, because I'd be curious to know. But I'm sure it is dozens before he even started soliciting designs from the public.
Okay.
Yeah.
Okay. So do you want to tell us a little bit more about Formlabs?
Yeah, absolutely. Yeah. So Formlabs is a 3D printer company. We've been around for a little over 10 years now. We spun out of the MIT Media Lab in 2011 or so. From there, we've branched off into two main 3D printing technologies, SLA and SLS. And as you can see on screen here, this is a kind of sampling of all of the different worlds we currently play in with our 3D printers, from manufacturing, medical devices, aerospace, education, dental, medical, research, consumer devices, entertainment, automotive, all kinds of stuff. If it's out there, we probably make a material that's designed for it. So a big part of what Daniel was trying to figure out as well from his end, and I know we have some materials on the next slide as well, is just choosing a material, because we make all our materials in-house. They're all designed to play very nicely with our machines. So unlike some 3D printers, which are obviously great for a lot of people, we try to minimize the amount of fuss that needs to happen with our printers. There's not a lot of bed leveling or things like that. We make the software, we make the hardware, and we make the materials, and they're all designed to sort of mesh very nicely together to minimize that back and forth. And yeah, this slide. Oh, go ahead.
I was going to say that, I mean, with the portfolio of materials like this, it looks like there is something very specific for just about everything there. You know, it's not just about making a prototype of shape. It's about making it work in an engineering situation too, right? So
absolutely. And the ability to bounce between materials quite quickly. So on our machines, you can switch between materials in less than 30 seconds. So having a few of these different materials you see on screen on hand, depending on the material characteristics and properties you want out of your parts at the end, is really important. So for Daniel, and he can talk a little bit more about this, I think most of where he was playing in was these engineering resins you see in the middle of your screen. This includes our tough family and our durable family, which mimic ABS plastic and polypropylene plastic. I will tell you that internally, whenever a new video came out where the propellers were being tested, we all had a moment of bated breath in the office, hoping that this wasn't the one where one of these propellers broke. And I don't think in any of those videos, any of these propellers had those issues, which was amazing. So yeah, we were really, really excited to see how well they did.
And maybe it's a good time to bring Daniel back on, because we do have a couple of questions there around how many did you make? What was the...
Well, I started out with the just testing different sizes of the baseline propellers, and some of those were FDM printed. Probably had 20 of those, and then throughout the competition, probably 35 SLA printed propellers. So definitely around 60 total propellers. So yeah, a lot of printing, a lot of materials.
And you did, I mean, I did watch the videos, and there were some designs that were more susceptible to kind of breaking or, the strength issues. Did you play much with materials as well to try and address that, or did...
No, funny thing, the only propeller that I can recall that actually snapped was an injection molded glass filled nylon propeller. It was like a really thin airplane propeller, so that kind of makes sense why it snapped, because the blade profile was like 1 or 2 millimeters. But yeah, none of the SLA resin printed propellers broke, which it amazed me. And even after the competition, I put those things on my towboat to pull me on a surfboard. And I'm putting like 800 watts into each prop, and they still held up. I even got the winning prop from the competition. I got a tube machined out of stainless steel with the intention of putting a lot more power into them. And I had those on my towboat, and I was curious. I was like, well, so they're working great, but if I put the resin printed propellers back on here, like they'll probably, I thought they would shatter. Sure, they didn't. So it was pretty incredible. And those were with the gray resin.
Okay, I know that one in there. Cool. So that's interesting for the just the sheer amount of printing that you got done there. And I know that there were multiple episodes of this series, and people were sending in probably redos, or there was all sorts of things going on there. That was great. So moving along, it was about this time that one of these other threads I talked about kind of intersected here, and I happened to see this model because it's a public model, and one of my colleagues showed me, said, hey, look at all this cool stuff that's going on. And I saw this, big, long design table. Now, what you're not seeing is that there's probably 250 more lines on that table off the bottom of the screen. And, to me, and of course, I use Onshape a lot as head of product. It's near and dear to my heart that something like this will trigger one word in my mind, and that is automation, right? This is an absolute textbook case of an opportunity for automation. So Austin, you and I separately outside the competition, of course, because the competition is already going on and people are watching YouTube by this point, but you and I got talking. Can you remind people or just to tell people about that?
Yeah, I mean, I recall working with Nacho and him sending a few emails back and forth, and I didn't expect, anything to come of it. And then like 2 days later, I got this almost completely current to what's live now feature that would just ingest all the data the way that my book describes it being needed to be formatted. And I was just kind of like, at the time, looking back, I like the way we polished it. We worked on it for like 2 months, and adding all the bells and whistles and niceties, but like I was like, this is finished.
So
this is excellent.
Yeah, cool. No, I mean, it certainly triggered something in me. I like doing these kinds of automation projects. I like using Onshape. So just to fill people in who might not be fully aware of this, Onshape is a parametric feature-based CAD modeling platform, amongst many other things, right? So we're looking at a propeller part, and it's got a number of features in it. And some of those features, whether they're sketches, features refer to variables, which are coming in from this table on the right-hand side. And there are many, many variables that you are using to control the position of the points along the curve, right?
Yeah, there's about 20 unique data points for every airfoil. And what the table allowed me to do is just paste them in. I transposed them from the array in the book. I could actually paste flick from an Excel document into the Onshape table, which is really convenient. And then that would just process all those 20 numbers into 20 dimensions that I could put on the Bezier curves, because the purpose of the format is that it's supposed to be usable in CAD programs, which 99% of have this Bezier curve. So it worked exactly as intended. The crucial part is Onshape had all the bells and whistles needed to do the translation for the data.
So let me tell you about.
If you're manually entering it in, it's not helpful. But if the table's there, it's great.
We'll get there, right? We're going to get there. I'm taking people on a journey here, right? So we're looking at this. We're looking at a big table. You can do it, right? You can regenerate this. You can change a few of those 250 numbers and have everything update parametrically, which is great. But when I saw this, I saw an opportunity. And tell us a little bit briefly, you know, we can go into it in a couple of slides later, but there is a book, right? There's a book called the Holbrook Aerospace Airfoil Vector Format, right?
Yeah, great name.
So yeah, it's
a little bit long.
A little bit long to say. VF.
Yeah.
And this is what I had to look at, and I saw the opportunity to take data and create a companion feature using Onshape's custom feature capabilities. You know, we have a language that we developed as part of Onshape called Feature Script, and with Feature Script, we can create custom features. It's the same language that we use to create the normal features in Onshape as well, extrude, loft, fillet, right? But we can create custom ones. So what Austin's kind of been hinting at is that we created a HAVF profile feature, which takes all of the dirty work of that table and puts it in a nice user interface. And I was doing this anyway because I was building some radio control gliders right at the time. That's why it triggered me just out of serendipity, right? So I built this feature and showed it to you, and yeah, here we are. You know, this is the feature which is now published. It's available publicly. You can get it now if you lean in and get that QR code. You can be building HAVF profiles within minutes. So what does the feature do? Just take us down some of the user interface here quickly.
Yeah, what the feature does is just any line, any mate connector, you can select it and put this vector-based airfoil on it, and it'll stay glued to that line or mate connector no matter where you send it. So normally when people deal with airfoils, there's popular websites like airfoiltools.com, and it's been coordinate based, you know, forever. So that means it's really rigid. You scale things once and it's hard to deal with, you know, the trailing edge scales with the rest of the design. And here you actually have the option to, you know, keep the trailing edge a consistent size or let the vector control it completely and have it scale uniformly. And there's all sorts of bells and whistles, like you can flip the direction, you can mirror it across the chord, and you have the option to use the small library, which is sampled from the book, where you can input any custom airfoil HAVF vectors that you wish to kind of create airfoils that nobody really has yet. So I published a YouTube video yesterday on how you can make your own vectors and your own airfoils. So that will work to make airfoils that nobody's seen, you know, for anybody that wants to try that.
Yeah, so we'll share all these links right in the description below, but also I think coming up soon, we will actually flash that link up. And these QR codes, links to Daniel's website and YouTube, you know, everything will be shared as part of this. But here, this is an interesting one because this is a comparison before after something, right?
Yeah, so you could see kind of the worst part of the template was just me making it. Nobody that used it had to make it, but like just drawing all of the splines and hooking every control point to an equation and getting that consistently done on the table to the point where there was no mistakes in it and it worked. It would hardly be practical even for me just as one person, but it was a great kind of showcase of what it could do, and if it was more optimized. And that's kind of what the feature is it's completely taking all that. You don't have to build a spline that's perfectly constrained with dimensions anymore. You can just select a line and select a mate connector, and all that's taken care of for you. And there's 0 rows of custom data. You can input the same exact custom profile or a profile from the book, and it takes, I modeled this in hours, where I was kind of, working on this other model over several days. So it's kind of turned it from a novelty into a really powerful tool, because you have all the geometry data over here in a really fast way to ingest it, and it works really well.
Yeah, exactly. And then it fits in with this ethos of making things publicly accessible, sort of on an open source. But your information is protected. Mentioned the book a couple of times. There are some information available about that. There's a YouTube tutorial, as you mentioned. What does this tutorial dig into?
Well, this video is different than the one I mentioned that I published yesterday, which was how to make your own airfoils. This tutorial is basically how the feature works.
Okay.
So that anybody can basically explaining what we worked on. And then it goes in a little bit, it talks about the purpose of the vector format and just how well it scales, like automatically updates based on chord or angle of attack, and just goes over the book a little bit about how it removes all the entropy possible from the most popular online airfoil databases, which makes it possible for me to do this fitting process where I can describe all these points using Bezier curves. So yeah, just a kind of tirade about that.
Yeah, no, I was obviously motivated and excited to work on this thing. But while all this is going on, millions of people are watching a design competition. And Daniel was doing a bunch of testing, creating graphs, and coming up with an ultimate winner, which I guess it's a competition. So Daniel, do you want to come back and talk a little bit about some of the takeaways from the design competition? All right. Do we have Daniel? There we are.
There we go.
All right. Yeah, there we go. So yeah, how did it all shake out? What did we learn?
Yeah, well, for me, kind of the biggest takeaway was that there's a lot of novel designs out there, but the true designs that just look like normal old propellers are kind of, unfortunately, what worked best. It's a little bit more boring that way, but it's the way it is. And one of the really interesting things is that propellers that look more like airplane propellers are actually performing better underwater. And that's probably only true at the lower RPMs and lower speeds that we were working at for the competition. But the winning propellers kind of looked like you just pulled them right off an airplane and stuck them on a boat. So that was really interesting.
I guess I guess there'd be some practical limitations, though. For container ships and things, you wouldn't expect to see gigantic, long, thin, slender propellers because of robustness and the chances of hitting things. And so the engineering has got a lot of trade-offs, right? And that being one of them.
Yeah, you would need some insanely strong materials to pull that off. And then also at large scale, I think cavitation would be a huge issue for those propellers, because they would have a super high tip speed, and higher tip speeds mean more cavitation. So yeah. But anyways, more takeaways. CFD is super useful for stuff like this, and it can really reduce your number of iterations. But if you don't have access to that, if you just have a 3D printer and a lot of time to waste, you can iterate all you want and kind of avoid the need for CFD. So that's kind of what I did, especially with baseline propeller.
So some people did use CFD, though, I understand.
Yeah.
And
not to discount CFD.
Was the AirShaper submission, right? That did really well. And I even used them for my submissions as well. And that helped a lot improve my design algorithm. So we've all been learning during this whole design competition. It's been really fun.
Yeah, not to discount CFD, because AirShaper and Friendship Systems, they used an iterative design process that was creating its own CAD models and automatically running them through CFD and iterating thousands of times. So they won with that method. So I'm not saying CFD isn't good, but for us hobbyists that don't have access to that sort of thing, you can get pretty far by 3D printing and testing and repeating the process, driving back and forth to the lake 100 times. My last takeaway was that the method I used for measuring the efficiency of the propellers for this competition was for system level, but what it basically gave us was the winning propeller for this boat at this speed. It was a system level test, and it doesn't necessarily give us the best propeller design in general. So what I've learned since then is that there's other methods of measuring propeller efficiency that I'd like to explore for future competitions that will hopefully kind of give us more of the best propeller design in general, separate of the specific test conditions that we're operating in. So I've been emailing some naval engineers about new methods for the future that I'm excited to start exploring.
It was interesting. I looked in the comments, and it seems like a lot of professional propeller designers or people got sort of drawn into this and have provided or contributed a lot to the whole competition as well. I mean, that was pretty cool.
Yeah, for sure. It's it's a huge process for me. Like I am not an engineer. I didn't even go to engineering school. I'm just a tinkerer, if you will. So I've learned a lot and continuing to learn, and I'm hoping to make season 2 a lot better than season 1.
Although there's going to be a season 2. That's great. Good to hear.
Yeah, hopefully.
Yeah, I mean, I added these next ones. That engineering is fun, right? That the whole process of solving problems or coming up with a way of creating, testing, and validating everything it looked like it was a lot of fun for you out there on the lake. It was a lot of fun for 2 million plus people watching along, and inspiring probably a lot of people to get out and tinker. So that was definitely something I took away from it. It looked like you had fun.
Yeah, I love this stuff. I can do it all day.
Yeah. The other thing that really stood out from the way that you did this is that you need to follow the data. Like that, intuitively, some of these designs looked like they were going to be cool, or looked like they were going to be fast or efficient, but the data doesn't lie, right? For this type of thing.
Yeah, I think a lot of people kind of got let down because everyone deep down, they want some sort of crazy, novel, organic, like nature-inspired looking propeller to be some magical solution that outperforms everything else and becomes the future of transportation as we know it. But sorry, guys, the data says that run-of-the-mill propellers are kind of what works best.
Yeah, specifically 2-blade, normal boring propellers.
Mm-hmm.
Yeah. Okay. Yeah. No. So it's great. And moving on to some other takeaways. Again, from my point of view, watching this from the side and then participating just on a parallel track. What was really interesting is that with Onshape being as part of it, you can access Onshape anywhere, right? You can access it when there's a web connection and a cell phone or a mobile phone, a mobile device, a Linux device, a Chromebook, whatever. So that kind of fits in with the open source. Let's get everybody involved, the team sport part of it. The open source nature of that public document that Austin first shared probably opened a door to many, many more people who otherwise wouldn't have had a chance to participate. And collaborating, if you haven't used Onshape, you can collaborate purely with links. You don't need to. In fact, you don't really want to send a file, right? There's no such thing as a file of an Onshape file. It's a link, and the link can be shared securely. It can be shared publicly, however you choose to do it. And I think as you probably have guessed from here, it is high-powered CAD. It's serious professional level CAD that you have access to, and has incredible automation capabilities, which I hope I demonstrated through that working on that custom feature with Austin. Dan,
and what I like about it is changing. It's changing the fastest. I've worked with other CAD programs that have been kind of similar for like the last decade, and I look forward to see where Onshape's going, because I don't think it'll be in the same place a year from now.
I know. There'll be 17 more releases by the time we get
Yeah.
this time next year. So that's how it goes around here. Dan, what did you learn from all this?
Yeah, thanks so much. Yeah, I mean, I'll reiterate some of what I mentioned in my slides earlier, but yeah, materials matter. If the output material of the manufacturing process won't stand up to the rigors of the testing or production environment, then it's not a useful material to use. So I'm glad we can offer that. Removing guesswork, like I said, just trying to cut down on the things that waste people like Daniel's time in terms of using a 3D printer that we'd rather people not be spending their time on when they could be using that time to iterate these prototypes. And lastly, the quality of the final product is our biggest goal. We want to make products that produce amazing objects for people. And the last thing I'll mention here, which wasn't added but has come up in this conversation, is one of my favorite lines in engineering, which is garbage in, garbage out in terms of 3D file. And that's continues to be true. If you don't have a really good input file to print, none of what we do matters. So I think we like Greg was saying, this is a really collaborative process where without companies like Onshape, PTC, or any number of others, we don't exist as a company either. So
Dan,
yeah,
I'd like to expand that even one little level further, in that the Onshape itself was, you needs ideas going into it, right? And that's the people. I mean, that the inspiration for what you want to get out needs to go in the other at the start. So whether you're printing something, you need a good idea. This is what you need to. I want to create. I can input that to a Form 3 or Form 4, and then have something great come out the other side. Same with Onshape, and I think that's a really nice part of this engineering process. That it's all about crafting from the system level down. These inputs are going to, and then make their way down the process, down the chain, and come out with some really interesting and fulfilling results.
Yeah, exactly.
Yeah. So at this point, we are going to turn it over to you, Dan.
Great.
To have a look at some of the multitude of questions that are coming in now. I'm only just going to quickly take a glance over myself, and wow, yeah, there's a lot. So, Dan.
Yeah, absolutely. Yeah, we've been keeping track of the questions as they've been coming in. Thank you guys so much. Feel free to put questions, whether you're watching in I'll mention the Formlabs YouTube channel or the Onshape one. We are watching both, so feel free to drop your questions in. Yeah, this is a question. I'll jump it to Daniel first, but then Austin, if you have any input as well. But we've gotten a few questions about multimodal propellers that could potentially be used for air and water. Daniel, have you looked into that? And what considerations would you kind of have in mind if you were starting a project with that as a goal?
Wow, that's a tough one as far as an engineering challenge. Water is 800 times more dense than air, so yeah, it's going to be very tricky. I would say that the best approach to that would just be to make a motor that can like shift gears or something to work at a different ranges of resistance, because it's going to be really hard to make a propeller that can work well in both. You just need to spin it slower for water.
I guess on that note, we also got a question, which was, if we're mostly talking about water, when you're designing for air, what are the main things you're thinking about? And it sounds like you started to get into that, which is like the ability to spin way, way, way faster. But what else are you thinking about when you switch to air?
Yeah, air is tougher from a materials perspective because the propeller is spinning so much faster. It's undergoing a lot more stress just from inertia, pulling the blades outwards, centrifugal force. You kind of have to consider the strength a lot more, at least for like drone propellers that need to spin at about that RPM, whereas our water propellers were spinning relatively slowly. Yeah.
And I guess, Austin, from your perspective, you've obviously written this book. Did your book focus chiefly on one or the other? Did you think about the differences between the two as you were?
It's kind of actually, the book explains kind of, an airfoil is kind of like a misnomer, and it's mostly a book about foils, whether you're operating them on Mars, in the water, but it is a good, interesting question. Like, why do we have the airfoils that exist now? The library that's out on the internet, how did people come up with those? Why are those the geometry that we landed on? And it's basically because of our atmosphere. Mm-hmm. So like they produce the surface level, density and, viscosity of air and water mostly determine what airfoils work better. So if you're doing airfoil optimization, that creates, the Mach and the Reynolds that you need to optimize around. And if we had different density of air and water, we probably have completely different airfoils. So it's a interesting, the book itself is a collection of geometry, and it would be completely different if we lived on a different planet.
Yeah. As you guys were saying earlier about like we're all waiting for some secret propeller design, but if Boeing or Rolls-Royce hasn't come up with it at this point, there's no like one secret that doctors don't want you to know out there.
There's some interesting companies coming up with mostly boat propellers. I think is it the Sharon or propeller? There's some application for it, but there's also a lot of debate around that. And I think Daniel went over some of the testing and actually talked to those companies in one of his videos. So it's hard to prove that you can't do something, and that's really what I think we'll be struggling to do for decades, if not forever. Absolutely. So there's always people willing to try.
Next question. This is one that's a little outside of my engineering knowledge, but someone mentioned flow attachment is critical. Can you speak a little bit more on that as you were designing? Daniel, I'll pass that to you first.
Yeah, this was kind of one of the fun challenges I had to solve for the video. For the production aspect is like, how can we kind of visualize the flow around these propellers? And a lot of the like university test tanks and stuff that they use for propeller research, they'll just inject dye into the water, which is definitely probably the best way to do it. But I can't just be injecting dye into the lake all day long. So I came up with a little mechanism that pumps bubbles into a symmetrical airfoil on the propeller, and then we can see the bubbles flow over the blade. And that gives us a great way to visualize, whether the blade is stalled or kind of what's going on with the vortices. And I didn't use that during the actual competition itself, like during the data collection, because the bubbles will interrupt the flow. They're basically just voids that are flowing through the propeller, and they'll probably make it stall more easily. But after I actually did all the data collection for the competition, I would go back, stick the GoPro underwater, turn on the bubbler, and then film. And it was some really beautiful imagery. Like when the camera's shutter speed perfectly syncs up with the RPM of the propeller, everything just appears static, and you can just see the flow. And yeah, it was just some amazing imagery. And you can kind of perfectly see when the blade is stalled, the bubbles kind of propagate along the core of the propeller, and you can see the vortices just like frozen in time. That was amazing. So yeah, definitely the best propellers don't have any flow separation. Yeah.
Awesome. I saw someone ask about designing propellers with a single blade and considerations for 3D printing and design for something like that. From the 3D printing side, I'll mention quickly, like the issues you'd run into are sort of the natural output of the design process, I think, for a single bladed design, which is like, you've got weight on only one side, you're flinging that weight back and forth very, very quickly. So that's the main consideration. For the 3D printed side is just making sure that the weight works out for a spinning propeller and that the material can stand up to a kind of single-sided weight model. But Daniel and Austin, I'll kind of pass it to you guys for how you think about single-bladed, and if you did.
Yeah, there were two submissions for single-bladed propellers, and the first time the guy submitted it, and it had no balancing. Like, center of gravity was way off the center of rotation. And I was like, bro, this is gonna destroy my boat. So I messaged him back, told him he had to balance it. So he did, and basically just added cutout holes in the side with the blade so that the center of gravity would, be in center of rotation, but still just the center of thrust being off of the center of rotation made it vibrate terribly. So yeah, that did not work out for the competition. I didn't get any good data for either of the one-bladed propellers. I think one of them actually broke. I can't remember.
And Austin, on your end?
I'm more interested in propeller acoustics. After seeing the zipline video that Mark Rober posted last year, because I tested a few single blade propellers, and there's never like that 5%, like a significant percentage, and it does come with that you have that huge counterweight on the other side that kind of kneecaps all the hope that you're willing to get rid of interference and improve efficiency. So but since the zipline video, I've been more interested in doing non-symmetric propellers, like propellers with 3 or 5 blades that they don't have the same blades, but they're balanced. Actually posted some prints of a 5-blade propeller where every single blade is different, and I'm going to be testing like the acoustics of that, and that's much easier to do now because you can have 3 or 5 airfoils per blade, and like up to 25 airfoils in a part, and you can manage that now pretty easily with the feature, and you can just tie it all to a plan form, adjust the plan form, and know that the airfoils are going to stay consistent. So I think that's where the more interesting evolution will be in the next couple of years, is seeing non-symmetric propellers, just because of the acoustics. You don't hear that blade pass every 50 degrees, and it avoids that harsh buildup of like a high-pitched propeller whine, especially in small drone propellers.
Because basically the different blade shapes are breaking the air, simply speaking, in like different spots, basically, or in different ways.
Yeah. So, and that's what the zipline propeller was going over. And I think specifically smaller drones are going to get really popular. Like the Neo is releasing, and the Avatas have been really popular. And those have really annoying propeller sounds, like they naturally spin at like over 30,000 RPM. And it'll be interesting to see what kind of solutions people come up with to avoid that kind of shriek in your ear as you're trying to take a picture with your family with your new DJI drone or something.
Awesome. Daniel, a question for you. Have you experimented with input or output vanes to see the effect on performance or efficiency?
Yeah, what I've kind of learned from my boat testing stuff is that water is so viscous that the more stuff you have in the water, the worse it's going to perform, at least at small scales that we're operating at. At the large scales of like cargo ships and stuff, I think it's different, and they'll put vanes on the propeller, kind of make it a ducted propeller a lot of the time. But at smaller scales and our smaller Reynolds numbers, especially at higher speeds, you just want to have as little stuff in the water as possible. So any sort of vane or duct is just going to ruin your performance, especially for speedboats. That's why a lot of the really fast speedboats have surface drive propellers. They don't even want the lower unit or the drive unit to be in the water. They want as little as possible. Only the very back little section of the hull and the propeller itself is touching the water when those speedboats are at speed. So yeah, ducts are fun to think about, but in this application, at least for the stuff I'm doing, they're not optimal.
Got it. Greg, here's a question I'll pass to you first, and then maybe we can go over it back to Daniel. But this person's asking, do you do a lot of testing and simulation? And if so, what testing applications are most compatible with Onshape? So just to you, are there any kind of the simulations that people would be using for these types of tests if they don't have a lake to test in? Do you have any recommendations for them?
Yeah, so there's a number of CFD application partners. If you go to the App Store of Onshape's App Store, right, you'll see a bunch of names, and a couple of them have, well, one of them at least, the AirShaper. There's has been mentioned today. The other one that we did use during some of this testing, SimScale. They have a really nice connection with Onshape as well. There are many, right, and we don't have a built-in native CFD application. We are using third-party partners for this. So yeah, that's probably the best way to look at that. Go and have a look at the App Store and yeah, make your mind up there.
Awesome. Here's a fun one. Austin, maybe I'll pass this to you first. A ring frisbee requires an airfoil that works in both directions. Does your book help with bi-directional airfoils?
That's something I haven't worked on in a long time, but if essentially you can, because there's a zero thickness trailing edge capability, you're mostly like tools like Xfoil, you're really only describing the top and the bottom surface. So if you have a zero thickness trailing edge, there's no limitation to giving the second X2, Y2 coordinate and the last, Y12, X12 coordinate. There's no limit on making both of those X values 1 and forcing a tangency on the trailing edge and then mirroring all the coordinates, over the half chord. So you can use the language itself to optimize propellers that operate in both directions, but you have to kind of understand the book goes over how it all works, and you can use the vector language to optimize airfoils. And it's an interesting question because the book itself is kind of like a latex dump of a library that I use in my own optimizations. So it's a good question.
Awesome. For both of you guys, but we can start with Daniel on this one. How would you design a surface piercing propeller, which might be just what you were talking about a moment ago? Do you see a lot of optimization potential for such propellers, or are they too simple with the absence of cavitation?
I don't know anything about them. Honestly, I know that some of the really fast ones, they don't even use airfoils, as you would call them, but they're just like wedges, because they need to have super cavitating blades. So they're basically designing the blades to cavitate, because any sort of a normal airfoil that has a sharp tip would cavitate, and you can't avoid that. So you might as well just optimize the blade for operating at cavitation. So they are very interesting, and I would like to maybe explore that for a future competition or a future video at least. But yeah, for right now, I don't really know much about them.
Yeah, I just had to look it up as well, full disclosure, and it is exactly what you just mentioned, where the water level is meant to pass through the hub of the propeller during motion, which is cool. I didn't know, but that makes perfect sense. Question here: what is the best material for propellers like these? Daniel, if you want to jump for a second and just like how you ended up with the materials you were using from us, and then maybe I can talk for 10 seconds more than that.
Yeah, so I printed most of these propellers with the gray Pro resin, and then with the Form 4, I switched over to the gray resin. And you really just want to find something that has a good balance of rigidity and durability, because you want the blade to be rigid so that it doesn't deform, and you want it to be durable so that it doesn't just snap. And gray resin are pretty much perfect for that. And you also really, you need it to not warp as it's curing. That's pretty important.
Definitely. Yeah, I would echo all of that. And just mention that the reason why Daniel switched to our gray from Gray Pro is because the newest iteration of regular gray is stronger than our old Gray Pro. So that's why that swap over happened. Awesome. I think we're getting down to it on questions here, but here's a good one. How much of propeller acoustics is due to blade design versus the BLDC motor whine in your experience?
That's a good question. I think it depends on the ESC, because ESCs have done just as much evolution as propellers have, or if not more, over, I don't know, since 2015, whenever quadcopters became popular. But if you have a loose magnet in your brushless motor, I mean, that could definitely start rattling around. Even the rigid structures of like the iron bell of the motor can start resonating. So it really just depends if you're hitting any resonance frequencies or not in the electrics or the rigid structure of the motor. But propellers can also resonate too, and it's hard to differentiate structural resonance from any aeroacoustics.
Awesome.
Yeah, what I
go ahead.
found, the cavitation was extremely noisy with some of the high aspect ratio airplane propellers, and the motor whine, the brushless PLDC motor whine was like, some of the propellers were really below the noise floor of the motor noise, so they were super quiet. But then the high aspect ratio propellers, the cavitation was just like ear-poppingly loud. So it was that kind of blew me away, honestly, like how much of a difference the cavitation makes. So as long as you can minimize that, then you'll have a pretty quiet propeller.
Awesome. Maybe we'll end on this question. But Greg, for you, and this, I think this is kind of general, and you've spoken on this a little bit, but any kind of general recommendations for how to combine Onshape with CFD programs?
Oh yeah, just building on that last one. There are a number of partner apps for this, but Onshape has a lot of great geometry creation tools that you can use to kind of prepare yourself for, and really prepare something that's going to go nicely into a partner or a CFD app. And in fact, I did some of this myself, and I got interested along with the rest of the world on toroidal propellers and started building some of my own using Austin's work as well, and found, when we want to have a moving reference frame around the propeller, and that's a common thing to do in a CFD code, to do this MRF type of moving reference frame with cavitation solution at the same time. It's always easier to do that in the CAD platform because you can make it parametric. And so when you're changing things quickly, then you can also get that, the boundary and the domain to be updating at the same time. So, it's just a natural extension of the modeling that you're doing in Onshape already. And then any number of really, really nice applications will be able to slot in really quickly to that. So the recommendation is to think about the process, thinking about how you inevitably are going to be doing a lot of iteration and a lot of changes. So think about that so that you don't have to keep starting from scratch each time.
Awesome. Well, with that, I think we will bring this webinar to a close. I want to say thank you so much to everyone who joined us this morning to watch this webinar, and to everyone who's here in the call with me, Greg, Austin, Daniel, and everyone who's working behind the scenes at our respective companies. Really appreciate your time as well. And yeah, thank you so much. This was great. For anyone who wants to learn more about Formlabs, we'll jump to this next slide here with all these QR codes. You can go find us here to learn more about the Form 4, or contact our sales team, and we'll figure out if Formlabs is right for you and your project. And I'll pass it over to Greg.
Okay, thanks everybody for today. It's been a great discussion. I hope we can get back together after season 2. So thank you very much.
Thanks, everybody.
Bye.
Thank you.
Thank you.